Hello, Greg is here. Imagine that you are a butterfly collector. You look for rare butterflies and you put them in this little box on your table under glass. And suddenly you find yourself at a meadow in which there's hundreds or maybe thousands butterflies that no one ever saw in the world. No collectors have them, and you can catch as many as you want. But when you start catching them with your net, you suddenly understand that the net changes those butterflies. Under the net, they change their shapes and colors. They change the net itself. And if you're not surprised yet, then you learn that your net is actually in the shape of a soccer ball. And no, I didn't smoke anything. I'll explain what I mean in a minute. So by soccer balls, I meant the molecules that are named fullerenes, and those are spherical molecules made of carbon. Chemists that discovered them got Nobel Prize for the discovery in the 90s. Despite the Nobel Prize, no much practical use were found for those molecules. But at least for one thing, they are very useful in the chemical research, and that's in encapsulating molecules. Still, no practical use for that, but very interesting stuff. Why it's interesting? There's almost no way that you can take a single little molecule, like, I don't know, a water molecule, and study it by itself without other water molecules surrounding. There is such possibilities on surface, but pretty hard. But you can really put one single water molecule inside fullerene and see what it does, how it behaves. And if you want to put a water molecule inside fullerene, you usually use the approach which I called here approach 1. Make a fullerene, you open it, you press water inside of it, and then you close it by chemical methods. And that's really what people do. There is also another approach when you create fullerene around molecule from scratch. How people create fullerenes. They take graphite, hit it with electrical current, and graphite layers close into spheres. So what kind of molecules can you create by this method? Today I want to show several works about capturing some compounds with uranium. But why would you choose uranium? Sounds dangerous, right? Well, not really. A good thing about uranium and other metals around in the periodic table down there among the lanthanides and actinides is that they are able to interact with the fullerene from inside. Water molecule cannot, but uranium can, and that actually helps the fullerenes to shape, to close around it. The method: take the graphite rods, you take source of uranium in an arcing chamber, you create fullerenes with uranium and some other atoms. Each specific compound which is created has different polarity, and you can use it to separate on the chromatography. So I'll show several examples of those butterflies that were caught inside the soccer balls. First, they try to catch carbon atoms with uranium inside the fullerenes, and those are two publications from one reaction. So they did one reaction and then they isolated one by one two different compounds. One with 2 uranium and 1 carbon atom inside, and one with 2 uraniums and 2 carbon atoms inside. It's all validated by multiple physical methods like mass spectrometry, quantum mechanical calculations, and other methods. In each case, it was a very different molecule with 1 carbon atom. According to the analysis, it has a carbon atom bound with double bond to each of the uraniums. This is the X-ray structure, by the way, and to obtain it they use this ligand. So they add this big molecule to interact with fullerene, and that makes it crystallizable. You see here also the interaction of uranium with the cage from the inside. That's also very helpful because it prevents the molecule from rotating inside the cage. So yeah, one paper was in 18 in Natural Communications, another one in JACS 2019, and in JACS there were 2 carbon atoms, and it's completely different structure based on bond lengths, based on orbital arrangement, many other methods. It's actually a triple bond between carbons and uraniums bound to this triple bond from each of the sides. None of those molecules could be observed in any other method. No one even know they can exist, and I don't think they expected to see something like that when they performed this reaction. After capturing those 2 with carbons, they tried to add nitrogen and to see what happens when you add nitrogen. And again, two different molecules in one reaction. Each one was separated, and each one was published, one in JACS in 21 and one in Nature 22. So in this case, we have a uranium-nitrogen triple bond, and interestingly, this uranium-nitrogen moiety absorbs charge of +2, and the 2 electrons go on the surface of the fullerene. In this case, they capture 1 carbon and 1 nitrogen on 1 uranium. And this carbon-nitrogen ligand called cyanide. Perhaps you heard this name. Uranium cyanides are known, but the cyanide never connects with both carbon and nitrogen to one atom. It usually connects only with carbon or with nitrogen, but not with both in the same time. And usually between carbon and nitrogen there's triple bond. They say that also here it's triple bond, but it's very long. Again, a very unusual thing that never could be seen outside of Fullerene cage. They published a paper in 23, very recently in JACS, and now to the carbon and nitrogen they added scandium. I think I know why they added scandium, but it's going to be on the next slide. So what did they get here? Again, completely crazy structure, never seen by anyone, with triple bonds from carbon to the uranium and also partial coordination with 2 scandium atoms. Interestingly, nitrogen has 1 electron less than carbon on the outer shell, but still it's the same structure in both cases. And not only that, the molecule with nitrogen is supposed to be paramagnetic. Nevertheless, they don't see an electron paramagnetic resonance. Well, uranium is problematic for paramagnetic studies, but still very interesting stuff, very interesting clusters, unseeable things. Why do you think they added scandium? In my opinion, it's just they wanted to add some transition metal, and transition metals are here in the periodic table, and they just started from the first. That means we should and can expect more publications with all the other transition metals one by one systematically, papers in JACS, Nature Chemistry, Nature Communications, and so on. This is a real gold mine. So to summarize, I've shown those beautiful structures today, that each of them was separated and isolated and crystallized and analyzed to the smallest detail. In one reaction, those 2 fullerenes were obtained. In one, carbon has 2 double bonds, 2 uraniums. Here, 2 carbons have a triple bond, 2 uraniums are connected to the triple bond. In the second reaction, where nitrogen was added, there is a cyanide connected to uranium with a very unusual arrangement of atoms. And in the second structure, there is a triple bond between nitrogen and uranium, and the charge from uranium goes on the fullerene. And in this fresh paper, there is a completely never seen thing with 1 uranium, 2 carbons, or 1 carbon and 1 nitrogen, and 2 scandiums. Also interestingly, you can see that in each case the fullerene has different amount of carbon atoms. It varies from 78 to 82, and I really look forward to see what they will come with in their next publications. Please write in the comments which structures would you like to see locked inside this cage? Which other butterflies would you like to catch? And what interesting properties you think such molecule can have? Okay, thank you very much for the attention. Please don't forget to like and subscribe to the channel, and don't forget to support Ukraine. Thanks. See you next time.